Yeah.
Okay, so hello, I'm Jessica Manning. I'm the Executive Director for MCB, and it is my pleasure to introduce to you Doug Richardson. Doug is the Director of the Harvard Center for Biological Imaging, otherwise known as HCBI, which is located in this building on the second floor. And if you haven't had an opportunity to check it out, I encourage you to contact Doug for a tour. He actually didn't recommend that I offer that up, but in case there is interest, I do suggest that you do so. So Doug has been a valuable member of the MCB community and the Harvard scientific community at large for since 2013. In addition to that, he's been a lecturer in the department, and it is greatly appreciated that he has offered to give a talk today on how a microscope works. So with that, I'd like to turn it over to Doug. Thank you, Doug.
Great, thank you, Jessica. That's on, you can hear me? Yes. Excellent. Great, good, so thanks everyone for coming in today. Thanks also to everyone who's stopped in the hallways the last couple of weeks and said they were looking forward to this, because that really put the pressure on to do a good job. So you can see I brought props, I've got PowerPoint slides, so we'll see how this all goes. Before I get started, I just want to mention, for the last 10 years, I've had the absolute pleasure of working with two of the best microscopists in the world. One of these gentlemen you obviously know very well, Jeff Whitman, one of the professors in our MCB department. And the other one you probably have heard of if you're interested in microscopes in any vein, and that's Jeff Appel, who I worked with for 3 years before I came. Not only are both of these gentlemen incredible microscopists, but they're also really good teachers. So basically everything that I'm going to teach you today has been taught to me by them. And so hopefully I can convey these ideas as clearly and as well as they do. So first of all, I want to ask a couple questions. Does anybody here, did anyone here have a microscope as a kid growing up? Wow. Okay. Does anybody still have a microscope today at home?
I got two.
Okay, so you're all more qualified to give this talk than I am. I never had a microscope growing up. I had one experience with a microscope when I was in grade school. I think it was when I was in grade 5 or 6. My best friend Justin had got a microscope as his birthday present. And so went over to his house for an afternoon, and we were so excited. We're like, oh, we're going to see things we've never seen before. I think we found like a dead housefly, threw that underneath, saw nothing but a big black blob. Like, oh, it says oil on the objective. Let's pour some oil on there, and grind that objective into that fly. Didn't see anything other than a big black blob. Let's try some grass. Nothing. So my ideas of the microscope is this amazing thing that could open up insight into the biological world was crushed, and we went inside and played some Sonic the Hedgehog. Genesis and shit. So that was the way it was until high school. Then we do those, everybody does those experiments in high school where you get a piece of onion and you get that thin layer of cells and put it under the microscope. You take a toothpick, scrape some cells off your cheek and put those on the microscope slide. Didn't seem all that exciting to me either. And I never really got into microscopy until I got into grad school. And when I got to grad school, my supervisor at the very beginning gave me a choice of two projects. One was kind of like a structural biology, protein structure function type project. It didn't seem that interesting. And another one was a microscopy-based project. And she showed me these images of these beautiful fluorescence images of these brightly colored cells. I said, that looks pretty cool. I'm going to try that. And since then, I've been hooked. And so hopefully by the end of today, you will be. So I'm going to talk to you today about light microscopes. And I'm not going to talk about electron microscopes, which are what we use for seeing very, very small things, but I am by no means an expert in the area of electron microscopes. So if we're going to talk about light microscopes, we obviously need to know a little bit about light. And there's a lot of different ways to describe light, different theories and methods that physicists have come up with. And I think the most obvious one is to describe light as a ray. This is the one we're most familiar with. So this idea that the light comes from some sort of light source, like the sun, and goes out in these straight lines and these rays that are going all over the place. It's very intuitive. It makes a lot of sense. I can stand here, I can make a shadow on the screen if I block the light from the projector. But unfortunately, there's a lot of areas where that idea of a ray or a beam of light just doesn't hold up. So we can also talk about light as being a wave. And this is, we can look at different ways where we can interfere light. So we can interfere two beams of light, and we can make them brighter or dimmer. Just like two waves in the ocean can combine to get bigger or smaller. Okay? You're probably familiar with describing light as a wavelength. So different colors of light can be referred to as different wavelengths. So we can have violet or blue light, that's around 400 nanometers, all the way up to red light, that gets closer to 700 nanometers. So I'm going to avoid talking about waves today. I'm going to try and talk mostly about rays. But another way that we can talk about light is this idea of quantum optics. And this is where it gets really complicated and complex. I'll give you an example. Quantum optics is a black box. And if we look at this laser pointer, the light from this laser pointer, what quantum optics says is that light travels not as a wave, but as particles, so particles that we call photons. And these photons, what quantum optics is saying is that when these photons leave this laser pointer in my hand, until you see them on the screen there, those photons actually occupy every piece of space in this room. And some of them are in the future and some of them are in the past. And we have no idea where they are. We can say a best probability, a best guess of where they are. We have no idea where they are until they actually hit that screen. So quantum optics is what we need to describe principles like how our camera on our phone works, how it's able to take the light in the room, convert that into an electrical signal, which you can then display on your screen. All right? So we will touch very, very briefly on quantum optics when we talk about fluorescence a little later on. But for the most part of today, what I want to concentrate on are rays. So what we're going to do is we're going to start with something very simple. We're going to look at a magnifying glass and how that works. Then we're going to move on to a traditional light microscope, so where you're taking white light, either you're bouncing it off a mirror or you have a little lamp down here, sending that white light through your sample into the microscope. Then we'll go into a fluorescence microscope, how that works. And finally, what we're going to talk about is a confocal microscope. So if any of you have done microscopy in the ACBI upstairs, you obviously know what a confocal is. It's kind of our workhorse. It's what we use most of the time. For those of you who haven't been in the facility or aren't doing microscopy, you've probably heard the term mentioned somewhere along the way because they are quite common. So believe it or not, to understand all of those microscopes, all you really need to know is what's going on in this little experiment here. You've probably all done this at some point in high school science class. So we have a little light box here that has a lamp inside, and we have these 5 little parallel slits cut in it. What that allows us to do is send 5 rays of light out of that light box. They're traveling parallel to one another, and they enter into this little piece of plastic, which is a lens. This lens is convex on one side, flat on the other side. This will also work if it is convex on both sides. So what you can see is as those rays go in and interact with the plastic, on the other side they get bent and come to a focus. So this type of lens here, where it's convex on one side or convex on both sides, there's a couple of different terms that are used for this. Sometimes it's called a converging lens, or positive lens, or convex lens. I'll try and be consistent and call them a positive lens, but if you hear me wander, that's what I'm talking about. So if we understand what's going on here, we can understand what's going on in all those microscopes, because for the most part, it's just a series of these positive lenses interacting with one another. Cool, so there's a couple of pieces of terminology that we need to know to begin with here. So obviously we talked about this. This is our lens. This is our positive lens, convex on one side, flat on the other. And there's an imaginary line that goes directly through the middle of this lens. Now remember, this is just a 2D cross-section of that lens. It's really a 3D object. And so there is a line that goes directly through the middle of that 3D object, and we call that the optical axis. On either side of this lens are focal points, and these focal points are the point where that light will converge. When you send parallel rays in from one side, that light's going to converge to the focal point on the other. So if I send parallel rays from this side, it converges to that focal point. If I send it from the other side, it converges to that focal point. You might hear me talk about a front focal point, or a front focal plane, and a back focal plane. The back focal plane is the side on which the parallel rays are coming from, and the front focal point is the side they're going to be focused to. Something very important is the focal length. So that's the distance from this focal point to the middle of this lens. And then of course we need some sort of object that we want to look at. So that object is going to be sitting on one side of the lens, and once the light that's hitting that object gets collected by this lens and projected to the other side, we're obviously going to have an image. All right? So that's some of the terminology that I'll be talking about today. Hopefully that all makes sense. If anything doesn't make sense, just interrupt me. Cool. So what's happening here? How can these light rays bend as they go through this lens? So this lens, like I said, this one here is probably a plastic. In a microscope, they're always glass. And what that means is the light is traveling through air, and then it comes in contact with this glass. And whenever light moves between different substances like that, it moves at a different speed in different substances. And this is indicated by something we call refractive index. So air has a very low refractive index, glass has a very high refractive index. And when light moves between an area of low refractive index and an area of high refractive index, it has the potential to bend or refract. Right? So what I want to do is, instead of looking at all 5 of these parallel lines, let's just look at 2 of these. And let's look at this first one that's coming in right at the middle of the lens. So when this one that's coming in right at the middle hits the lens, it's hitting it at an angle perpendicular. So this is a 90-degree angle right here to the surface of that lens. Right? So that light is going to go in. Because it's hitting at this perfect 90-degree angle, it's not actually going to bend or refract. It's going to slow down a little bit as it moves through the middle, and then it's going to speed up again on the other side and keep going straight. Something different is going to happen to this ray that's coming in here at the top. When it gets to the lens here, it's not hitting at a 90-degree angle anymore. You can see this is not perpendicular. And so you can really only explain this with waves, and I promise you I wasn't going to talk about waves today. But basically what happens is if this light's traveling as a wave, part of that wave starts to slow down when it hits the glass here, and the top of that wave is still kind of traveling pretty quickly because it hasn't hit the glass yet. And that actually is what bends the light. It's the same thing if you take a pencil and put it into a glass of water, it looks like it's bent. It's the same idea, it's all refraction. Okay? So that light ray is going to bend a little bit. It's going to bend a little bit on the other side as well. And then it's eventually going to come down to a focal point. And believe it or not, there's actually a mathematical equation that explains how much bending you're going to get here based on the difference between the refractive indices. I did take the time and effort to draw this correctly. So this is what you actually would get going into a glass line with these different angles. So now that we know that that refraction happens, there's a couple different rules that we can use if we want to figure out where an object on one side of the lens will appear on the other side of the lens. So basically, if we have an object sitting here and we've got a lens, and we want to put a piece of film or a little CCD camera on this side, where should we position that film or CCD camera so that we get a nice sharp image of this barrel? And so here are the rules. So the first rule is that any ray that passes through the optical center of the lens does not refract at all. Okay? So I'm going to draw that one. So this is exactly what I was saying before. If you have one of these rays that goes right through the middle, it hits at a perpendicular angle on that lens and just keeps going through without refracting. Okay? The second rule is any ray that starts out parallel to the optical axis, when it refracts at the lens, it's going to go through the focal point on the other side. Okay? Just like that. And then the third rule says that any ray that passes through the focal point on this side of the lens will then travel parallel on the other side. So that one goes through the focal point, comes out parallel on the other side. And now, you can see here's where our image is going to be. Right? So this is called ray tracing. Very simple. Again, you probably did this in high school. But this is how we determine where that image should be on the other side of our lens. So how do we actually magnify something with a lens? So if you take a look here, this arrow is exactly the same size as that arrow. There's no magnification at all in this system right now. And that's because this arrow is sitting at a very particular point. It's exactly 2 times the focal distance of this lens. So when we sit exactly 2 times the focal distance, we don't get any magnification of that arrow. What do I have to do if I want to get some magnification? Sorry? Yeah. So what happens if I move this a little bit closer? We just moved it just a little bit closer, not very far. And you can see now we're starting to get some magnification. Okay. So let's go to a really crazy example. So what I've done here is I've moved our object so close to our lens that it's inside the focal point. So the focus of the lens, then the focal point. So where is this image actually going to show up? Let's just take a look. We'll go back to those rules that we had. So our first rule was if we had a ray, actually this was the second rule I put in before. If we have a ray that's going parallel to the optical axis, it goes through the focal point on the other side. Then the first rule was that a ray that goes straight through the center doesn't refract at all. Let's try that one. Third rule was going through this focal point, which is going backwards, so that's going to be useless to us. So let's look at these 2 rays right here. Where's our image? Where do those rays come together? What happens if I look backwards? If I extend these rays back in this direction, they will eventually converge. And we have our arrow here. Highly magnified, it's a lot bigger. So this is what we call a virtual image, okay? So there isn't somewhere where I can place a piece of paper or a camera lens and actually see that, have that focused onto it. But what we can do is we can put our eyeball here. Our eyeball has another lens in it. It's going to focus that light onto our retina in our eye. And what we're going to see is this magnified image. Okay? This is how a magnifying glass works. So we just have one of these positive lenses inside the magnifying glass. We move it close to what we want to look at so that our object is closer than the focal point. We look to it with our eye, refocus these diverging rays, and get a magnified image. Great. So what are we going to do with our microscope? So I've shown you a couple different options here of where you can place an object. So we place something really close, and that gave us a lot of magnification. We placed something 2 times the focal distance, that didn't give us any magnification at all. We put something at 1.5 times, we got a little bit of magnification. Where do you think we want to put our sample in front of our microscope to get a really good magnification? Any ideas? So the answer to this question is it depends on the type of microscope that you're using. But most modern day microscopes that we use are called infinity corrected systems. And in an infinity corrected microscope, you want to place your sample right at the focal point, right here. So let's take a look at what happens if we do that. So here's our object sitting right on the focal point of our lens. And we're just going to draw those rays again. So here's the one that goes parallel, it goes through the focal point on the other side. Here's the one going straight through the middle. Oh no. What's going on? We're not focusing to a point here. We have a big problem again. Right? And you can see this is even worse than the magnifying glass, because these rays here on this side are actually moving parallel to one another. So we can't trace them back on this side and find a virtual image. But what's interesting about this is this was a great advance in microscopy, because the secret here is we can actually place another lens over on this side and collect these parallel rays. And we can move these lenses relative to one another, and it doesn't, let's say for lack of a better term, mess up our optical system. So here's what it's actually going to look like. Here's our sample plane where our sample's sitting, right at the focal point of this lens, which we're going to call our objective lens. Okay? And if we have an object sitting here, the rays coming from that object are just going to go straight through that lens. If we have an objective or an object off to the side here, pointing our sample off to the side, that's going to create parallel beam of light going in this direction here. We have one down at the bottom, it comes out at a different angle. So basically what this lens is doing is it's translating all of these different points in our sample into angles of light behind it. And what we're going to do is we're going to put another lens there. We're going to call this our tube lens. It is going to collect all of these parallel cylinders of light and refocus them back onto an image plane. So if we were to put a camera chip right here, we would be able to see perfectly our image that's sitting on our sample. We'll be able to see that image back here. Okay. This area in between the objective and the tube lens, this is what we call infinity space. And this is why this is called an infinity corrected microscope. And what it means is that we can move this objective up and down throughout our sample to look at different focal planes in our sample if we have a fixed sample. And it doesn't mess up the rest of the system. So we don't have to be translating our camera chip or our tube lens at all. It also allows us to put some interesting other optical elements into this space. And that's how we're going to design it for us. So, how do we get magnification out of this system? So again, the way I'm drawing this right now is this arrow and this arrow are exactly the same height. So there's no magnification in our system right now. So if we want to get magnification, let's just do this the easiest way. Let's make this arrow a little bit bigger and then draw the ray tracing in the opposite direction. So if we do this, something has happened. So the first thing you might say is that this point right here, the top of our arrow, is shifted closer to our lens. So it looks like we've just shifted our object closer to our lens, but that's not actually correct. So remember this, the rule for this ray that goes parallel to the optical axis. Where does it refract through on the other side? Has to do with this lens. It refracts through something behind that lens. It goes through the focal point, right? So see with the green one here, refracts through the focal point. So what's happened here is we haven't actually moved our object closer. What we've done is we've changed our focal length of our objective. Okay? So these two little red dots, those are now the back focal plane and the front focal plane of this objective. So to create magnification in the system, what we do is we change the focal length of our objective lens. So this means when you're going to higher and higher magnification objectives, you have to look at thinner and thinner samples and place them closer and closer to the front lens of your microscope. So if you're ever playing around with a microscope, that 10x objective sits a few millimeters away from your sample, and you never have to worry about crashing into anything. If you go to that 100x objective, it gets right down a few hundred microns from your sample. You have to be really, really careful with it. So that's how we get magnification. Cool. So if we put that all together, this little microscope here looks like this. So we have a stage where our sample's sitting on it, and we have light that emanates from a position in that sample. It goes through our objective lens, it gets turned into an angle, so a cone of light traveling on an angle. It goes through our tube lens, gets focused back to a position in our microscope here, which then we let that diverge again, and we capture it in something that we talked about earlier, the eyepiece, which is another lens sitting up at the top of the microscope. That then sends another angle or parallel beam of light into your eye, and we obviously have another lens in our eyeball as well, which then focuses that light back to the position in the eye. So all the microscope is doing is just taking information and changing it from a position to an angle, to a position to an angle, all the way until we get to a detector for your eyeball. So that's what's happening in this situation. We've got some light that comes in and bounces off this mirror, goes through our sample, goes into our objective, through the tube lens in here, through the eyepiece, and up to our eye. Cool. There's a couple problems with this. And that is what I showed you before was all ideal lenses, and an ideal lens doesn't actually exist. So there's always a few problems when you try to manufacture one of these lenses. Most of them are made by hand still. The highest quality ones are actually made by hand. Someone polishes that curvature with a very soft cloth. And there's two things that are going to happen that we're always dealing with in the microscope. And these are what we call aberrations. The two biggest ones are chromatic aberration and spherical aberration. So chromatic aberration arises when, I told you light can travel as a wave. And when a wave goes through this lens, depending on the wavelength of that light, it gets refracted to a different degree. So you can see that the blue light gets refracted the most, and the red light gets refracted the least. So if you're looking through a light microscope, this starts to look like little rainbows around the edges of your samples. Another thing that happens is it's really difficult to design and manufacture one of these lenses perfectly so that the rays of light that are close to the optical axis get focused to the exact same spot as the rays that hit out near the edges of the lens. You can see these ones hitting out near the edge of the lens are getting focused in front of where the actual focal point is for the rays that are close to the optical axis. This is something called spherical aberration, and it just makes your image a little bit blurrier. So I depicted our objectives as just this single lens up until now. And if you do that, you have to deal with all those aberrations. But obviously our objectives look like this, so this big metal canister. And if you cut this thing in half, what you actually see is there's a whole bunch of lenses on the inside there. This is that little front lens that I've been showing you before. And these are all the other lenses that are there to correct for all the aberrations that are caused in this one. All right? So some of these, there'll be two types of glass that will be sandwiched together that have different refractive indices. And that's one way to correct for chromatic aberration. Sometimes you'll see these weird lenses that are kind of flat on the inside and then bulbous in the middle and flat again on the sides. Those are lenses that are designed to correct for spherical aberration. So this costs you a few bucks on Amazon. This costs you tens of thousands of dollars from Carl Zeiss. Cool. Okay, so we talked about the light microscope. We talked about a couple different types of aberrations. What I want to talk about next here is the fluorescence microscope and why fluorescence microscopy is so important and why that makes up 99% of what we do upstairs. So this is a game that I like to play with the undergraduates. This is an image. This is just a transmitted light image, so we're just shining light through a sample. And that sample is made up of a bunch of really small beads. Okay, so they're 4 micrometers in size, which is about 4/1000th of a millimeter. And this entire field of view here is about a millimeter squared. All right, so what I want you to do is look into this image and find something that you think is one of these beads. Okay? These beads are actually fluorescent. So what I'm going to do is I'm going to switch this over to the fluorescence image, and we'll see if you found a spot that is exactly 4 microns in diameter. Okay? Everybody have a spot that they think is the bead? All right. Were you right?
No.
So the truth is, a lot of what you're seeing here is a lot of dust and things like that that are present in the microscope, even our 15 microscopes upstairs. But what you're seeing here is these fluorescent beads. And what I'm trying to convey to you is just the incredible enhancement you get in contrast with the fluorescence microscope. And that's why these are so popular and why we're using them all the time. So here's another example. Here's a piece of mouse kidney. So just a really thin section of a mouse kidney. Again, just with a transmitted light image, so just shining white light through it. And this is pretty good. You can see some pretty nice detail there. This image next to it, this is a bunch of endothelial cells. So those are the cells that line blood vessels with the exact same illumination conditions and everything. These are incredibly thin cells. You can't see anything at all there. All right? I'm going to play the same trick with you. I'm going to throw the fluorescence image over top of this. This is the exact same field of view. All I did was change the illumination, exact same microscope. There's our fluorescence image of those cells. Okay? In this particular one, we've used 3 different fluorescent dyes. A green dye on the actin filament, so the structural proteins holding that cell together. There's a blue DNA dye, which lights up our nucleus. And then there's a red dye on the mitochondria, so the energy centers of the cell. And again, this is just the same transmitted light image beside it. If you look really closely, you probably can't see it, but sort of this big actin bundle filament, you can kind of just make it out there. So obviously, fluorescence microscopy is fantastic for not only the contrast that it gives us, but our ability to attach all these different fluorescent dyes to different molecules in our cell. So now we can see with molecular specificity what is happening inside our sample. We can pick out a particular protein, a particular gene, just by attaching one of these fluorophores directly to it. So these fluorophores are made by companies now. They're very complex molecules and dyes, and they're readily available. But they also occur in nature. So what's going on with fluorescence? What does fluorescence mean? So here's 2 naturally occurring fluorophores, chlorophyll and beta-carotene. And these actually are highly present in olive oil. So what I want to do is show you over on this side here. I've got 3 little plastic cubes. And hopefully I have these in the right order. So the one on the bottom here, this guy here, is just filled with water. So what I'm going to do is I'm just going to shine this laser pointer through it, and you can't see anything, which is great. Oops. So if I just shine the laser pointer through there, you can see there's a little bit of a green dot on either side. That's just where the plastic is scattering the laser a bit, but there's nothing going through the middle. If we go to this one up here, can you see that? You can actually see the laser moving through. So the difference there is a few microliters of milk in there. The milk particles inside scatter the laser light so that it comes out at all different angles. That's not fluorescence. So if I go up to the olive oil here, so now you can see there's like little bright specks of green. That's just chunks of something that's inside the olive oil. So the olive oil hasn't been filtered through a fine enough filter, and some of that laser light's bouncing off of it. All right? That was with my green laser. This laser here, this is, you can see it's kind of a purpley bluey laser. We're going to do the same thing. Get the angle right. So you can see the blue light going in and coming out, but what color is it inside the olive oil? Orangey red color, right? That's fluorescence. So what we're doing is we're shedding in blue light onto this chlorophyll molecule that's sitting inside there. That chlorophyll molecule is absorbing that blue light, and then it's spitting it back out as red light. Okay. So this is where I said we have to talk a little bit about quantum optics. So if you're talking in quantum optics, what we're doing is we're sending in these purpley bluey photons of light, so these individual particles of light, but then interact with the electrons in this molecule. They interact for a very brief amount of time, just a couple nanoseconds, and then that energy is shot back out as a red photon, or a red particle. Okay? And fluorescence is awesome because we can now really start to take advantage of this in our microscope. So I showed you the chlorophyll there. You can turn blue light into red light. That's a really large shift. Usually most fluorescent dyes don't shift light that dramatically. This is another commonly used, we're going to call it a dye, but it's actually a protein. It's called the green fluorescent protein. It comes from jellyfish. Something that we commonly use in the facility. And what I'm showing you here is an absorption chart and an emission chart, okay, or histogram. And on the absorption side, this is showing you all the different wavelengths of light that can be absorbed by that green fluorescent protein. So you can see we can send in really deep UV light that gets absorbed well. The purpley bluey light from that laser pointer would be accepted to some degree, absorbed to some degree. But this sort of light blue cyan colored light is what gets absorbed the best. Okay? And once that light's absorbed, it gets spit back out as fluorescence, and that's the emission profile here. And you can see it spits out some of that light as cyan light. Most of it comes out as green light, which is why we call it a green fluorescent protein. And then we get a little bit of yellow and orange light as well coming out of there. Okay? If we overlay these on top of each other, you can see the light, hopefully you can see the light green curve here is the absorption profile. The darker green curve is the emission profile. And we can draw this line down the middle here that separates those two. Okay? And this line actually represents a special component, which I'm going to tell you about in a second. So if we just go back to this diagram again here, I told you this space in between our objective and the tube lens in our microscope, we call this infinity space. And it's really special because I told you we can jam some optical elements in there that are going to be able to transform this microscope into a fluorescence microscope. And the most important element is this little guy down here. And this is what we call a dichromatic mirror. So it's a mirror, but it only reflects certain wavelengths of light. Okay? And it's what's represented by this black line. So this axis here is percent transmission. So what that's saying is that any wavelength of light below, say, about 490 nanometers is not going to pass through that. It's going to reflect off of it just like a normal mirror. But any light above about 490 nanometers is going to transmit. So it's going to pass right through there. So we have a mirror that can reflect UV light and blue light, and it's going to let green light, red light, yellow light pass right through it. Okay. So what I can do is I can put that little dichromatic mirror right here in the infinity space in between our objective and our tube lens, and we can take some of this cyan light that green fluorescent protein really likes to absorb. It will bounce off of this dichromatic mirror, go through our objective, and go down onto our sample. And if we do this correctly, if we focus this light at the back focal plane of the objective, it actually comes out as a collimated or straight beam of light that illuminates our entire sample plane. And so now we're going to have a few of those green fluorescent molecules on there. They're going to absorb that light. They're going to give off green light. Some of that green light is going to get captured back by our objective. And now, because it's this longer wavelength of light, it's actually going to pass right through this dichroic mirror. So it's not going to get reflected, it's going to pass right through it, go to our tube lens, and onto our image plane. So what we're able to do is shine this blue light in onto our sample that excites our fluorophore, collect the green light coming off of it, pass it through this dichroic mirror, and send it to our camera. And this is something called epi-illumination. So, in fact, we have this dichroic mirror. It sits inside what we call a filter cube inside our microscope. And there's two other components that we add in there as well. So usually we're not shining in cyan light specifically, we're usually shining in white light. And so we have what we call an excitation filter. So this is a filter that's only going to let these wavelengths in the blue pass through it. So it's going to take all that white light that's hitting it, only let the cyan light go through onto our sample. Okay? So an excitation light goes in, bounces off this filter cube, goes down to our sample, and then our green fluorescence that's coming off comes back up, passes through the dichroic mirror, and then we have an additional filter on the top there that just cleans that light up. So this dichroic mirror isn't perfect. A little bit of the excitation light can still get through it. So we add a second emission filter just to clean it up quickly. So here's our more complex fluorescence microscope. So we have a lamp sitting at the back of the microscope that sends in white light. That light gets focused down to the back focal plane of the objective by a lens up here. And that white light comes in, goes through that excitation filter. We just pick off the green light. It bounces off this dichroic mirror, goes down, excites our sample. This is actually a red fluorescent dye that's shown here. So we get some red fluorescence coming from our sample. It comes back up, passes through that dichroic mirror, passes through the emission filter, and goes up to our eyepiece. So that's the guts, the inside of the fluorescence microscope. Now, there's a major limitation to a fluorescence microscope. And this kind of comes back to what I said at the beginning when I tried to crush that fly against the microscope and see something. A fluorescence microscope, or any light microscope, really begins to break down the thicker your sample gets. So we're used to this idea of preparing a microscope slide where you take a slide, put a thin sample on it, put a cover slip on top. But if this sample here gets a little too thick, we run into a big problem. So here's what in the microscopy world we would call a medium thick sample. So it's 50 microns in diameter, or in thickness. To put that in context, here's the thickness of a human hair. Okay, so still a little thinner than human hair, but to a microscope, this looks really thick. We have a microscope slide underneath that's usually about 1 millimeter thick, so it actually extends off the bottom here. And our cover slip on top, as long as you're using the right cover slip, it should always be 170 microns. So if we take a look here, if we're using a really high resolution objective, the focal plane that we're looking at is only as thick as this red line. Okay? So everything here is drawn to scale. So all we care about is the fluorescence from this thin line. But because we're shining light all the way through that sample, any fluorophore sitting above or below is going to contribute out of focus blurry light to our image. That's really going to degrade it. And then, if we wanted to image through this entire sample, so let's say we wanted to start with our objective nice and high, and move our objective down through our sample and keep snapping images as we took that, and build that back into a 3D image, it's going to be very difficult to do that. This is actually what it's going to look like. So this looks horrible. So this is a big hunk of tissue. I'll tell you what it is in a second. But what you can see is something that we call in the microscope, we call the point spread function. So that says that a single point of light, once it gets back to our detector, it actually looks like this ugly hourglass shaped mess of light. Okay? So with this, we're always collecting light from all the focal planes. It's all just becoming this messy, blurry object, and we can't see what we actually want to see. So what we need is a fluorescence microscope that can take an optical section. So what do I mean by that? So here are two examples of the blurry images on the bottom right-hand corners of these images. And on the top left now, I've shown you optical sections. So just a thin section that actually matches the depth of field of that objective, of what the objective actually wants to see. And so this is there's kidney tissue again. You can see now, once we get this nice thin section, you can actually see these red blood cells really easily. And over on the other side, these are those thin endothelial cells that I was showing you before as well. And you can see we get rid of all this out of focus blurry light and get a nice sharper image. So this is exactly the same idea as an MRI or a CAT scan, where we want to be able to put a sample, in this case it's someone's head, under an imaging device. And we want to be able to take a bunch of sections of it that we can turn into a 3D image without actually cutting that person out, or in our case, cutting out a microscope. Okay? And the way we do that is with a confocal microscope. Now, the confocal microscope was originally designed by a gentleman named Marvin Minsky. Has anyone ever heard of him before? He's actually really famous for artificial intelligence. He's often considered one of the grandfathers of the artificial intelligence domain. But he actually spent time as a Harvard Junior Fellow across the street in Pierce Hall. And this was something that he designed way back in 1957. He actually patented it back then. The patent ran out long before we actually ever put this into production for biology, so he never made money or fame off of it. But if you take a look at this complex diagram, the important part of all of this is this little thing right here. So this is a little barrier with a gap in it. It's called a pinhole. It's just it can be as simple as a piece of cardboard with a little pinhole stuck in the middle of it. And this is ingenious in that it lets us filter out all of the out of focus light from our system. So if we take a look at this diagram here, it might be tough to see, but I have one molecule of that green fluorescent protein sitting right on our sample plane, and these solid green lines are the ray traces from that point. And you can see that if we move them back to the microscope, we put one of these pinholes just in front of our detector. That light from the focal plane is in focus right there, and it passes right through that really small space of the pinhole. But if we take a molecule that's just slightly outside of that focal plane and we ray trace it with these dotted lines, it actually gets focused in front of that pinhole, and most of the light is diverging by the time it hits the pinhole, and it just gets filtered out and never makes it to our detector. The exact same thing would happen if I put this plane on the other side. So what we're doing now is using this pinhole to filter out all the light except what is coming right in the middle. We also do this a little bit differently. Oops, sorry. Instead of illuminating the entire sample all at once, what we're doing is just illuminating a single pixel at a time. There it goes. So what we're doing is, I'm just looking at this region right here, we're just scanning a laser beam back and forth, building up that image one pixel at a time. So if we do that, this is actually slower than it actually happened. We scan that back and forth, move our objective a little bit, scan it back and forth on a whole bunch of different focal planes, then we can build up a 3D image. So here's that terrible image that I showed you before that was just done in wide field. Here's the exact same area, the exact same sample done on a confocal microscope. This was a nice little present from Aaron, our new imaging specialist. And you can see it's just these beautiful neurons. You can see the cell bodies. You can see the axons and dendrites projecting off of them with very high spatial resolution. Okay. So this is what the inside of that confocal microscope looks like. It's complex, but it looks complex, but it's actually pretty simple. We have a bunch of laser lines that come in. These little discs here are our dichromatic mirrors that our light bounces off of, goes down into our objective. We create some fluorescence there that comes back into our objective. We can pass through these dichromatic mirrors. It goes over here. This is our pinhole, which we can, in a fancy microscope like this, we can control the size of it. And then it bounces off some optics in here and eventually ends up on our detector. Okay. And this is, we actually have 4 of these sitting upstairs in the facility. And that's what people are talking about whenever they say they're going to use confocal microscopy. So what can we actually do? So I'm just going to give you a couple examples, just working through those types of microscopes that I mentioned. So first, with just a transmitted light microscope, this is what we call a wound healing assay. So these are a bunch of cells that are sitting on a plastic dish. It's actually a dish with 6 different valves. On a nice automated microscope, we can monitor all of them at the same time. What we do is we just scratch some of those cells with a pipette tip, and then image them over. This was overnight imaging to watch them grow back in, heal that wound. And the cells over here are identical to these ones, except they have one single mutation in a single protein that inhibits their ability to move. And you can see that while this wound heals up, no problem, this one here is still open over the same time point. So these movies are running in parallel right now in real time. So that's a simple experiment we can do just with transmitted light. These are 2 really cool images of fluorescence imaging. They're just on a single plane, nice thin samples. So this is a mouse brain section out of the macros lab that's been stained with 4 different dyes from 4 different components of the neural tissue that's in there. And on the left is what we call a tumor microarray. So these are tumor samples from a number of different patients that have then been stained with 4 different markers. And you can start to get an idea of whether all these tumors are the same or whether they're different just by looking at the different colors expressed in them. These are a whole bunch of confocal images, so 3D images that we can look at these cool little marine animals called acorn worms. We can look at pollen. We can look at parts of spiders. You must be later what part that is. Or we can look at development. So these are C. elegans embryos starting out at just 4 cells and growing over time and dividing into more and more cells as they develop. And then finally, if you want to do the king of all experiments, you take an entire organ. So this is a whole mouse brain. It's gone through a chemical treatment process to turn it optically clear. And then we can put it on a special confocal microscope, which we call a light sheet microscope. And in about 3 hours, you can image that entire brain and produce this 3-dimensional image. So this is a mouse brain that's expressing that green fluorescent protein. It's under a specific promoter called the 5-1, and this is a mouse line that's been generated by the scenes in the labs. Cool. So as you can see, my voice is about to leave me. So I will end with a marketing plug by saying that if you're interested in microscopy, or anyone in the lab is interested in microscopy, feel free to stop by. We're just up on the 2nd floor. You'll find myself up there. You'll find Aaron, the imaging specialist, who's sitting up here, and Christian, who's our Dyson embedded specialist as well. And I just want to close by saying I live in this interesting world somewhere between science and administration. So for all of the scientists in the room, thank you for all the cool and interesting samples you bring us on a daily basis. It's an absolute pleasure to see all this stuff. It's so wonderful not to be tied down to one project and actually get to experience mouse brains and bacteria and everything in between. And to all those people on the admin side, thank you for putting up with my scientific tendencies and helping me out with everything that you do over in that area. And thanks for coming out today.
You mentioned that the blue ray is refracted more than the red ray. Is it due to the wavelength?
Exactly. You know how I kind of said I didn't want to talk about waves, but I said when that refraction happens, it's because part of the wave starts to enter the glass and slow down before the rest of the wave has. It's still moving quickly through air. So if you have a shorter wavelength, that effect is different than with the longer eyeballs. Yeah, so that's why. So when we're actually measuring refractive index, it's always done with say yellow or orange RGB to get rid of the effect of the component. I've used them, but I can't really know why. Point of oil immersion? It's a very good question. So every objective, on the side of it, there are two numbers that are stamped on the side. One is the magnification, and the other one is something called the numerical aperture. Magnification does not mean anything. You're acting crazy when people come in and say, I need 100 lens objective. It doesn't mean anything. What's really important is the numerical aperture. The numerical aperture refers to what angles of light can be collected by an objective. So a low numerical aperture objective can only collect a really narrow beam of light. A large numerical aperture can collect a lot. You always want to maximize that numerical aperture. That gives you a brighter signal, and it also gives you better resolution in your image. So what oil immersion allows us to do is your light is coming from your sample that's sitting underneath the cover slip. When that light comes out of the cover slip and into the air, there's a lot of refraction because there's a big index of refraction mismatch. So a lot of your light actually bends and misses the objective altogether. So that means you can't have a high numerical aperture with air, and you throw away a lot of your light. When you put oil there, oil has the exact same refractive index as that cover slip, so there's no refraction there anymore. You can collect a lot more light, brighter image, better resolution.
Do you ever use non-visible light in any of these experiments?
Yeah, really good question. So if you've ever held a flashlight up to your hand, obviously there's white light coming out of the flashlight, but when you look at the back of your hand, it looks orangey red. And biological tissue is really good at absorbing blue and green and even red light to some degree. Very poor at absorbing infrared wavelengths of light. So there's a technique that we use fairly often called two-photon fluorescence microscopy. And with a two-photon microscope, if we think of that example of the green fluorescent protein, usually we send one photon of blue light in and get one photon of green light out. We can send in 2 photons of infrared light. They have the exact same amount of energy as a photon of blue light. And if they hit that fluorophore at exactly the same time, we get that fluorescent process. So in that situation, we send in 2 photons of infrared light and get 1 photon of green light out again. And that has the huge advantage of the infrared light passes through the sample a lot easier. So we can image a deeper, larger tissue using a 2-photon image. So that's one example of it. We use UV light too on occasion. Certain blue dyes that we have are